Alright, so I'm going to just spend a little bit of time talking about a library that I wrote recently called PureScript tailrec for dealing with monadic tail recursion in PureScript. And at the end, so if anyone has any questions, we can spend time talking about, we can spend time going over questions. And the other thing I was probably going to just talk about was some of the recent additions to the compiler, because I think there's been quite a lot of pretty cool changes, so I'll go over some of those as well and try and give some demos. Okay, so PureScript tailrec is a library. I think I registered this in Bower, so hopefully I can open a new tab. I can try and create a new project to demo this. Okay. So pulp init, Bower, install PureScript tailrec. Okay, good. So it pulls in a few different dependencies. The main one is transformers. So the goal of this library is going to be to try and be able to do monadic tail recursion over the different monad transformers in the transformers library. And obviously, you know, it's the idea behind tail recursion being that we want to generalize, you know, regular tail recursion and keep the stack relative, you know, do things in constant stack space. So let's see. If I try and come up with an example, does anyone have a favorite simple tail recursive function that I can give a quick demo of? I'll try and, okay, let's think, what's a good one? I can do like factorial just as a really simple example. So, factorial of 0 equals 1, factorial of n equals n times factorial of n minus 1. Okay, so build with pulp. Okay, so it takes a little while because we're building all those dependencies, but that's fine. And then if we open this up in PSCI, we can hopefully just check that main facts 5, for example, gives the right answer. Okay, good. So the problem is, I guess this isn't the best example because you generally wouldn't have these values getting very large. Let's write a different tail recursive function. Let's do something that doesn't blow up quite as much. Let's do triangle numbers. So now if I say main triangle 5, it's 15. Okay, that's good. So these numbers I can pass in relatively large arguments, and hopefully it shouldn't get too big, something like n squared, right? Okay, good. But the problem is this uses a stack depth of size n, where n is the input to the function, right? So I'm doing a recursive call on every on every number greater than 0. So there's a standard trick we can do. We can pass in an accumulator instead, or we can do this with a helper function. So we can say triangle is the helper function, which I'll call go, and we pass in an accumulator, which is 0. We say where go of an accumulator on 0 is return the accumulator, and go on the accumulator in n is go on n plus the accumulator and n minus 1. Hopefully that gives the same thing. Okay, good. So if we look at the generated JavaScript for this, let's see, main index. I guess I didn't recompile. Oh, it's in PSCI modules, that's why. PSCI modules, node modules, main index. So you see this has been turned into a while loop here. So this is the PureScript tail call optimizer. Pardon me. The tail call optimizer is going to look for functions in which every recursive call is in tail position, like this one here. And in tail position means it's the last thing called by that function. And in this case, it is. So when we see functions like that, the compiler can actually go ahead and just turn that into a while loop like this. So you don't use you basically end up with a function that uses constant stack instead of linear amount of stack. Okay, so then the problem. So this is great, and this works in a good number of cases. There's two problems with this. So the first problem is that the PureScript compiler isn't smart enough in a lot of cases to figure out that a function is actually tail recursive. And the reason is to do with the way that things like case statements get code generated. We actually do the oh, it's like it's full. Oh, I didn't even realize this was like a Hangout. I thought there was sort of an unbounded number of people. Okay, never mind. Well, it's recorded anyway, so that's fine. So because of the way we generate things like case statements, and because tail call optimization is actually done on the generated JavaScript and not on the AST, which is sort of in itself maybe a bit of a mistake, some functions that involve in particular case statements don't get tail call optimization applied correctly. So that's problem number one. And problem number two is that this doesn't necessarily generalize very well to monadic tail recursion. So the one case in which it works nicely is if I write a function called triangle trace. So I have debug.trace imported here, and I'll also need control mono f. Oops. So in this case, I'm going to rewrite this to include the trace effect, and it's going to have the same result type, but it's going to trace its execution as it goes to the console. So we'll say where this is the exact same case, except now we need a return. And if we have a non-zero case, then we're going to use a do statement to trace. Well, we'll show n. We'll show n. We'll trace the accumulator, so it's clear what's going on, and then we'll recur. So add the accumulator, same as before. And -1. And we'll just change main to triangle trace of 10. Oh, wrong one. Forget the command. Is it pulp run? Pulp run. Okay, there we go. So if I run this. Now I should see, everything traced to the console, and I finally get my my answer of 54, which is good. I think that's correct. So maybe it's one lower, but that's fine. So if we look at the generated code again, so that was PSCI modules, node modules, main index. Hopefully this has also been. Sorry, again, these are the wrong way around. In this case I want output because I built with pulp. In this case triangle trace, again, okay, so in this case actually we haven't been able to do the tail call optimization. So you see that triangle was tail call optimized like we saw. This one still has an explicit call. It still has an explicit recursion call. And again, it's to do with code generation, because we do this tail call optimization on the generated JavaScript, and because of the order in which things got optimized, again, there's work that can be done on the optimizer, so maybe we can sort of get this into a state where the tail call optimizer actually can optimize this, but because of this is sort of guarded by this function here, the optimizer can't figure out that this was tail call recursive, so it doesn't bother to turn it into a loop, which is bad, because that means that this function still has linear stack usage. So so the solution, which I actually think is quite nice, in the sense that in PureScript we have a tendency to sort of try and solve problems in libraries rather than in the compiler. And it may turn out that this library that I'm about to show is sort of the basis of a new approach in which the tail call optimizer actually just gets removed. And it's nice because the tail call, in the current approach, if we look at the code, it's implicit in the code that this is a tail call here. You have to look, and for a very complicated function, while it might be obvious for this function, you would have to look and figure out that this was a tail call. So the actual behavior of the function at runtime is not sort of explicit in the code, or at least not immediately explicit. With the approach taken in a library, you have to jump through a little bit of a hoop to get this to get the constant stack usage, but it's absolutely crystal clear that what we're doing is a tail call recursion, and it generalizes nicely to the monads. So okay. I'll go over that now. Let's see. I think there's some module documentation in here. Nope, not that one. Source. Okay. So here's the documentation. So there are two main functions in this module that are interesting. So here's a function tailrec that tries to sort of capture in a function what it means for a function to be tail recursive. So notice that in the source code here, let's see, source main. So I said that something was tail recursive if every return point, every recursion point was in tail position. So thinking about it another way. Every time we return something from a tail recursive function, I either have to just sort of, like I do in this case, return a value without recurring, or I have to recur and pass a new value into my accumulator. So if we make the accumulator explicit, we can actually try and capture, we can sort of abstract over this pattern here, bringing the recursion all into one function, and that's exactly what the tailrec function is trying to do. So this says if you give me a function which takes an accumulator and either returns a value of type B or returns a new accumulator, I can loop on that function until the loop eventually hits a B, starting at this A that you gave me, and I'll loop until I give you a B, until I get a B and return it to you. So that means that if I import this module here, I can rewrite triangle, for example. I can leave this one here. Oops. So I can rewrite triangle instead of doing the recursion explicitly. I can call tailrec of go, passing 0 as the initial accumulator value. Go has to have the type number to either a number or the return type, which in this case is also a number. I need to import that module, tailrec. Let's see, what did I miss? So in this case, we're actually returning an actual answer, right? So we need to use the right constructor. And in this case, instead of calling go recursively explicitly, I'm going to call the left constructor. And I need to pass a new accumulator here. So let's see. Something's not quite right here because obviously I have two arguments. Let's see, go. Oh, this would be easier if I'd have picked the fact example or something, I think. Never mind. Maybe I should just start over here. Sorry, bear with me. Sorry. Okay, here we go. Okay, just check if there's any questions. Okay, so I'll call this example. I'll call tailrec to say I want to do a tail recursion with my helper function is going to be called go, and I'll pass in the initial accumulator value of 0, and I'll say where, again, go takes a number to my accumulator, so either a new accumulator or I'll do a string. So if the number is if the accumulator is 0, then I'll just return the empty string. Sorry, that should be right empty string. Say I'm finishing the loop. And if it's anything greater than 0, if it's anything greater than 0, then I want to recur, so I'll return a left. I'll recur on n-1. That gives me a string. Sorry. This is the example I'm trying to reproduce here. I'm sorry, it's actually been about 3 weeks since I've looked at this library, so sorry, bear with me. So the point is we capture this recursion explicitly. This becomes more useful in the presence of effects. So the point that I was trying to drive at was that we want to generalize this function, which captures this tail recursion, to a function which works over a monad at M. So instead of just returning an either AB, we return either AB inside, wrapped by this monad type constructor M here. And instead of the return value just being a B, now it's an NB. So both our function can have effects, and our final loop can have effects. And then we capture this in a type class that subclass is monad, called monadrec. So the nice thing about this is if we it's really easy because we have tailrec to write this for the identity monad, and it's also really quite simple because of the way the F monad is structured to write it for the F monad too. So we get instances of this for identity and F, but then the cool thing is we can actually lift this over standard monad transformers, so that you can do constant stack tail recursion for things like state T, writer T, error T, and you can combine these so that you can make a full application stack and actually write monadic tail recursive functions in some actually useful application stack. So as an example of that, so here's I'll just go quickly through the examples. So this is a very simple example using F, which is very similar to that triangle example that I had before. So here we we create a loop. We use tailrec M, and we pass this this action here. And again, see, so we use write to indicate that we're that the computation is done and we want to terminate the loop. But we can have effects in here as well. And we use left to indicate that we want to recur and modify the accumulator. So then the way in which various monad transformers actually get incorporated is, if I look at the source, it's kind of interesting. So here's the instance for identity, which is very simple. We just wrap the tailrec function. This actually is tail recursion as implemented by the compiler itself. So if this does end up replacing tail recursion as provided by the compiler, then obviously this needs to become a foreign function declaration. But then we can wrap that function, and that gives us tailrec M for the identity. Tailrec on the F monad is also very simple. We have to do a bit of FFI, a little bit of trickery to sort of like get the types in the right place, but then we can pass some helper functions in and we get an actually usable tailrec M for the F monad. Then things like maybe T get a bit more interesting. So what actually happens here is that we end up kind of inlining some of the monadic bind function in a lot of cases directly just into tailrec M. So the thing is, every monad is an instance of monadrec. The problem is that even though you can write something of this signature, there's obviously an inhabitant of this function for every single monad, right? We just sort of like lift up tailrec just use tailrec in the Closely category, I guess, instead of in the regular category or something like this, right? But the problem is the default implementation doesn't have nice stack characteristics, but we can write a type class that, it's sort of, its laws in inverted commas, its law is that the stack usage is constant. And the way that's actually, we end up, in order to implement that, we have to actually re-implement some of bind inside these instances. So if you look at this looks a lot like bind for the fragments of bind for the maybe t monad transformer, and the same with error t. State's a little more interesting because here we have to actually modify the accumulator type. So if we want to keep a state of type S, that's sort of equivalent to modifying our accumulator so that we tuple the accumulator with type S. So if you think about the accumulator as the state of your function, an accumulator is a type of state, then we're just sort of expanding the state that we use in our recursive function to include an extra part of state, an extra piece of state, and then we capture that. The type we expose is by using state t. But again, there's a sort of tower of calls here, and when you get to the bottom of your application stack, you're actually going to be using one of these, tailrec f or tailrec, and neither of these, both of these are tail recursive, and none of these use any explicit recursion. So that gives us constant stack usage for any of these monads. And then those examples that I was showing, just go through each of these. So we can do things with writer, so we can tell to an accumulator. We can throw errors in the error monad. We can get and put a state in the state monad. All these different types of things. So that's the brief overview. I don't think any projects are actually using this right now, but I would be interested to get people's feedback and see what people think. So that's it. Does anybody have any questions on that? Oh, okay. A mostly automatic feature in the compiler and replacing it with developer effort because the effective tail recursion case is hard to analyze automatically. Why not just use the library and cover the monad case and leave compiler tailrec as is? So I think, yeah, that's a very good point. So if anyone can't see the chat, there's a question that says, why not leave tail call optimization in the compiler for pure functions and only use this library for Monadic tail recursion? So that's also a good option. Like I say, the main problem as I see it is that it's really unpredictable. It's hard to predict when tail call optimization is going to occur right now. And this makes it very explicit. So that's my reason. And as people use this, if people try it out and people hate it, then maybe that's the solution. We keep tail call optimization in the compiler. I'm generally in favor of keeping the compiler as absolutely as small as possible. And doing things in libraries wherever we can. So, so if there's any case where we can do that, then I'm probably going to vote for that. But like I said, we'll see how it works out. If people don't like this approach, then we can leave it as is. Anybody have any questions? All right. Okay, so I'll probably, what time is it? Let's see. We've got half an hour, right? Yep. So I was going to do a quick demo of some of the more interesting features that have been added to the compiler lately, if people are interested in that. This. Okay. Let's see if I can pull up. So here's the release. Oh, actually, I should go back to a couple of older releases. Let's see. All right. So here's compiler 065. So this release actually had a lot of really nice additions. I'll probably just, for the most part, go over the enhancements because they're the things that are most easily demoable. But there's been 3 releases lately, and each one has some really nice enhancements, but also some kind of important bug fixes. So if only for that reason, I would recommend upgrading if you haven't already. And the other reason is that some libraries have actually been broken by some of these changes, so it's actually, depending on the libraries you use, kind of essential that people upgrade. Okay, so 0.65, first of all, has some really nice enhancements in the way of syntactic sugar for records. So this is something I actually haven't tried out a whole lot, so it'll be interesting to see, to try this out as I go, and we'll see how it goes. So just to make sure the PSCI on my path is the latest. Okay, this is 0.67, so this should be good. So let's see. We'll take the person example. So if I create a record in PSCI, Phil, last name, Freeman, location, Los Angeles. Okay, Control D. So then I can evaluate various things in here. So I can say person.firstname. Okay, good. If I want to do an update on this, so I can use a record update to do various updates. So one thing I can do is I can change the first name. So let's say John. And because I can't print objects in PSCI, I'll just so you know what? Let's just write a quick function. Let's say let's show person first name. Okay, good. So if I want to update this, I can use a record update notation like this. So I can say the first name is now going to be John, and his location has changed to San Diego. Okay. So this is good, but usually you know, these things aren't going to be constants. They're going to be provided as something like a function argument. So let's define a function. We'll say update first name, takes a person, and a new name, and it just updates the first name property to the new name. The type of that, let's see, update first name. So this is raw polymorphic. So it takes any record that has a first name property of type T4. Oh, that's unusual. Oh, okay, no, this is right. This is changes the type on update. And if we change it to a T2, we get a first name property of type T2, and both of these records can have a tail of type T3 of any other properties. So this is good, but so in particular cases, it's nice to be able to have a partially applied version of this function. So so one way of doing that is to just in the new compiler version is just to replace first name with an underscore. This is going to be a duplicate declaration, isn't it? So let's call it that. And now this should give me the exact same type. Okay, that's good. So in this case, this is actually this is the update, the object update for person on first name sectioned over the value that I'm going to actually update. So more interestingly, I can actually section over the person too. So again, I put an underscore in there. I remove the person. I call that update first name 2. And the type of that hopefully should be the exact same thing. So these are just desugaring into the function that I wrote up here. It's exactly the same thing. In this case, in the case of this section, the field itself, we're using the field name, first name, as the function argument name. And in this case, the object itself, we're actually going to use an automatically generated name. It's going to show up as one of those names that you see in the JavaScript. That's sort of an underscored number variable. So That's all about object updating, and then the other side of the coin is object getters. So if I want to write a function like get name person equals person dot first name, that has this type. So again, it's polymorphic in the type of the label and the type of the tail. But again, I can section. So I can section the record person this time. Remove that argument. Oops. I just realized that there's a feature here that I didn't realize existed, which is kind of interesting. You can actually separate function declarations for the same name over different different commands, which is kind of neat. Okay, so then type of getName1 has the same type. So again, we're just sectioning that function argument over just by placing an underscore in here. So it's important to note, first of all, this isn't full Scala-esque underscore. I don't know what they're even called in Scala, but sort of wildcards or placeholders. This is only possible in a few syntactic locations. So the three that I mentioned, I think this record location before an update, a field inside an update, and you can have multiple labels here with multiple wildcards, and a record in a getter like this. So this is useful. This is a really simple use case, right? You almost save nothing by doing this. But where this is really handy is in things like if I want to get a person over asynchronously in the continuation conti monad, like is described in the book for doing AJAX requests or something. So we'll say gets a person asynchronously. But I don't care about the whole person record, I only want the first name. Then instead of having to write a lambda here, this is kind of nice that I can just write this section. So I expect there'll be a couple of interesting uses for this, and I look forward to seeing what people come up with. But I think this is a really nice set of features that we've been wanting for a while. So this is actually related to another set of features, which is operator sections. So this is a feature that's pretty much just taken straight out of Haskell. So let's say we want to write a function successor, which takes n, we'll write it how I did it before, goes to n plus 1. Oops, sorry. Then the type of this takes number to number. But again, it'd be nice if we could, actually, I wonder if this works with the plus operator. I expect it probably does, but we'll see. It'd be nice if we could just section like we can in Haskell. And I think that now we actually can. Okay, good. I was wondering if this was going to pass as +1 or +1, but that's good. So you can section on the right like that. You can section on the left. Oh, sorry. You can section on the left. You can section on the right like this. So here we're partially applying the plus operator on the left, and here we're partially applying it on the right. And also you can section, let's think of a good example. Okay, I need a named function. Okay, cons should do. So I'll take the type of cons. Okay, so let's say I want to build a list. I could do that by saying 1 cons 2, and I hope I got the precedence right here. Cons empty. Let's see. No, I didn't. Okay, doesn't matter. This is one way we could create a list. If I want a function to just cons something onto the front of a list, I could do it like this. But again, it'd be nice if we could section this, and in the latest release of the compiler that's possible as well. Oops. Oh, yeah, the same error. Okay, so we can section operators, we can section infixed function names. One other change is that we can actually, this notation here, this backtick infix notation has actually been extended so that it doesn't have to be just a single function name now. You can actually stick any expression whatsoever in there and it'll basically just change it as if it was an infix function application. So this is quite nice, I think, if, what was my example? Let's say we want to do, we have a list of people, or we have a list of, let's say, heights and a list of widths, H's and W's, and we want to zip them with, so this defines a list of rectangles, a list of heights and a list of widths, and we want to calculate, we want to zip them together and find the area of the rectangles. So we could do it like this. So we'll say let rect areas of H's and W's equal that. Okay, well, never mind, zip width isn't in scope. The point is, this whole expression on the left-hand side now can be infixed. Just like this. Now, there's a bit of a trade-off here. This is definitely something that can be abused. We don't necessarily want people to, do things like nesting infixed things. That could get very complicated. But I think for nice, simple applications like this, this gives us a bit of expressive power that we didn't have before. And I think it could be a benefit. So this is marked as something that's experimental. And if people like it, it's going to stay. If people don't like it, we'll probably get rid of it. But I think it's quite nice, especially certain code has a sort of English reading when you can write things with backticks, and I think this increases the set of pieces of code that you can actually write that way. So it'll be nice to see what people do with it. Okay, question check. Nope. All right. So I forget what was in 6.6. Okay, so yeah, this was more of the wildcard functionality, and actually I covered. So I think I covered two releases here. So this was where the extended infix notation actually got introduced. 0.6.7 is quite neat too. This is the latest release. So this has a couple of nice features. Scope type variables is one of them. So this is something that's been on my list for a while, and I was sort of pleasantly surprised that it was actually easier to implement than I thought it was going to be, which was good. So here's the use case. Suppose we want to suppose we have a list type, just a standard cons list, and we want to write a map function. And the way that I'm going to do this is by using this helper function. So instead of recurring and keeping the argument f everywhere, I'm going to just close over the argument f and use, and f is going to be in scope in the body of Go. But the thing that I'm interested in actually recurring on is the list itself. So this is a fairly simple definition, but then the question comes: if I want to choose this structure for my code, how do I pick a type for Go? So the type of Go is it's just the partially applied function of map, but without this function here. So it's list A to list B. But the problem is list A and list B. I can't say it's for all list A and list B because it's not. It's for this particular list A and list B. And I can't mention the types of the variables A and B directly in the type, or at least I wasn't able to. So the only way around this previously was to use a wildcard. So a wildcard basically used to say to the compiler, generate a fresh unification variable and solve for it. So I don't necessarily want to tell you what this type is, or maybe I can't tell you what it is because it's a scholarmized type, like a rigid type variable like this. So I won't specify it, just figure it out, and hopefully you can solve that problem and everything can compile. But the problem is, this works, but it's not very expressive. You can only express a portion of the type signature. So with scope type variables, you can actually use types A and B in expressions that are sort of scoped by this for all here. So in particular inside where bindings. And this also works in, so if you introduce, basically any way you introduce a type signature like this or by a type annotation, anything that's scoped inside that expression has access to those type variables. So it just means that you can give more precise types to your programs if you're using polymorphism. So that's quite neat. And the next thing is the ability to use rows in instance contexts. So the actual use case for this, here's one example, but the use case that I had was if we want to use a state monad transformer, and we want, or for example, we want to use the monad state type class to capture monads that use a particular type of state, but in which the state was a record. So there was a restriction previously that you weren't allowed to use, that rows weren't allowed to appear in instance heads, which I still think is a sensible restriction, because the whole point of sort of extensible records and extensible effects is sort of that, you know, no particular label is special. Like a label doesn't have any sort of semantics attached to it. You know, unlike in Haskell, for example, where record labels come with a data constructor. In PureScript, they don't sort of have any. They don't belong to a particular data constructor, and because of that, they don't have any semantics attached to them. So I think it's wrong to sort of give an instance in which the instance head mentions, you know, a row with you know, a non-zero number of labels. So functional dependencies sort of like make that question more interesting, because you can ask the question, well, is it fair to write an instance head in which the rows are only solved for, they're not actually used for you know, directing type inference, and maybe that's another avenue to look at. But the solution for now that we came up with was that it's perfectly fine to put rows in instance context, but not in instance heads. So I can't define a type class instance for this, for example, directly, but it is reasonable to use it on the left-hand side of a type signature as a constraint. So that allows us to do things like use monad state for a state type which is a record, and it also lets us do things like this where I want to, you know, write a type class monad f that captures things that can lift effectful actions, and then constrain my monad so that I always have the ability to lift trace actions, for example. So I think this could be kind of neat, especially in conjunction with the f monad and effect rows. So we'll see what this gets used for. Then there's two more things. So let bindings, this is something that I've been kind of showing a little bit of while I was coding. So let bindings in PSCI have changed a little bit. So previously they would get desugared into local lets in the function you were declaring. Now they get desugared into top-level declarations in your module. So that means that you can use all of the things that you can put at the top level now. So you can create data declarations inside PSCI. You can do foreign imports inside PSCI. And one thing, like I said, that I just realized was a feature that I didn't realize before, was that you can actually do multi-case declarations even in single line mode, which is kind of neat. So PSCI, I think it's single line mode. Okay, so I can say let fact 0 equal 1, let fact n equals fact n minus 1 times n, type of fact, okay, fact 5. Oops. Did I miss something there? I don't know. Oh, I need to look at that anyway. So the point is we can do more interesting things inside PSCI. We can do data declarations and foreign declarations and all these kinds of things. Okay, and then the last thing is PSC docs has been expanded. Now we can include Markdown inside the code comments, and it gets inserted into the documentation. So if you want to use Markdown, just to align the comments, because we have a mixture of line comments and block comments and all these kinds of things, you just have to use a pipe character to say where the left-hand side of your document is, basically. So it looks a little bit like Hadoks, but the pipes extend all the way down. And then this Markdown here is just going to get inserted right into the generated documentation. And then related to this, I've been working on a project recently Let's see if I can find it. Contour.com, PSC pages, called PSC pages, which actually generates HTML documentation and takes, let's see if there's a good example in here. So it takes the markdown from the comments and actually generates HTML. So this eventually, you know, I want this to converge on something that looks a little bit like Hackage, but we'll see where this goes. You know, maybe people are interested in contributing. That would be really great. But so this is another example of the markdown being used for documentation. So that's it, I think, for the last few releases. Does anyone have any questions on any of that stuff?